So again, hi everyone. Thank you so much for coming today. Today we have Oiku, who's going to share with us tips and tricks and show us how exactly to write our mathematical models using Python, talking to CPLEX. And yeah, we will, just like in part one, we will go through the theory, and afterwards we will go into breakout rooms and we will try the exercises by ourselves. So it's highly encouraged that you have your CPLEX working and that you at least get to write the exercises. But Oiku is going to guide you on that too at the end of her presentation. So Oiku, the floor is all yours.
Thank you so much, Rose. So hi, everyone. In case we haven't met last week, my name is Oiku. And today I'm going to show you how we can build a model using CPLEX. So let me just go ahead and share my screen so that we can start. I don't know if you're able to see it. Oops, not sure. Does it work? Yes, no? Perfect, okay, great. So let's just get started right away. So before I actually get into what we can do with CPLEX, let's just have a quick recap of what we learned about last week and how these are going to be actually useful for us this week. And also just as a sort of like an overview of what we're going to cover, this is going to be a very introductory presentation for those of you who have never used CPLEX with Python before. So if you have done this before, you might find the things that we're going to cover in this presentation maybe too intuitive. So yeah, that's just something that I want to clear out of the way. And regarding the things that we've done last week, we've actually looked at a bunch of different things about Python, just like data structures, list comprehensions, functions and modules, and random number generation, which we saw were all very useful for different purposes. We can use random number generation to generate instances. And of course, reading these from a file or writing them to a file are things that are going to be useful for us. And as we're going to see in a couple of minutes, we will be using functions and list comprehensions pretty intensely when it comes to using CPLEX with Python. So these are going to be really useful concepts for us in this presentation as well. Okay, so we have 3 different very innocent looking points that we're going to go through today. I'm going to talk about IDEs and what these are and how they're useful. Then I'm going to move into building and solving your very first model with CPLEX and the things that we need to know about, again, covering the very basics instead of getting into details about advanced methods. And finally, we're going to learn a little bit about debugging and checking whether our model actually works correctly. Sometimes part 2 can get a little confusing and complicated if our models are big and confusing. Part 3 is actually really, I think, important to make sure that step 2 is just clear and everything works in part 2. Okay, so let's see what an Python IDE is. So an IDE is an integrated development environment. And if you've done programming before, if you've worked with a different language, or if you work with Python in other applications, you probably know what I mean by this. It's sort of like an editor that will allow you to edit a .py file. And it just has nice features to basically write your codes and structure your codes and create packages if you want to go down that route. And also when you're debugging, it will offer you some really useful features, basically. So when we're working with optimization models, it might be a good idea to look into IDEs because when you're writing big optimization files, Jupyter notebooks might not be sufficient in terms of the things that we're wanting to do. It's still an excellent option to test things out. It's still an amazing way of learning small bits of code. But when we're talking about maybe multiple functions or multiple models defined at once, you might prefer this over Jupyter notebooks in the upcoming sort of journey of your research. So a great option for this is Pycharm. If you want to download it, you can just follow this link. I believe it's already you already have the presentation, so you should be able to click that and follow the link and do the download yourself if you wish to do that. Okay, so the exciting part of the talk today is going to be this, basically, the building and solving of optimization models. We're going to be talking about this in great detail today. And before I move into what we mean by building a PyCPLEX model and how we can go about building a PyCPLEX model, I will first give you sort of like an example template of what your model, or what your Python file actually, will look like. The very first thing that we want to do is actually to import the modules that we're going to use. And of course, since we decided to use PyCPLEX, at least in this presentation, it's what we're going to be covering, we will have to import the PyCPLEX module. And for this, we will have to have PyCPLEX downloaded, and you will have to have followed the steps that actually were in the instruction guide earlier about linking PyCPLEX with Python for that to work. And of course, on top of this, we're going to have other modules at the very beginning of our code, like JSON, pandas, random, NumPy, many other things that are very useful for us. And once you've done this, we're going to move into the inputs part of things. We're going to initialize all the data that we need to use in our optimization model. And again, there are different ways you can go about doing this. So you can either decide to read data from a file, or you might want to generate data using maybe the random module. Or you can just initialize data inside your Python file if you want. And this is actually the route that we're going to be following today. And as for building the PyCPLEX model, we're going to get into the details of every single bullet point that you see right now today. So we're first going to start with initializing our PyCPLEX model object, and we're going to learn about how we can sort of add different variables and constraints and parameters into the PyCPLEX model that we've just created. And once we create the model, of course, the only thing that's left for us is to solve it and then retrieve the solution information after we're done with solving it. So that's just going to be again, the main focus of today's talk. And once we're done with everything, of course, we might decide to just write our results into a file along with other useful solution information. So it's something to, again, keep in mind. So like I said earlier, today we're going to focus on the PyCPLEX module. We're going to initialize data as we go. We're not really going to look into reading data or generating data since we've already done that in the first part. And the main focus again is going to be on the build the PyCPLEX model block. And we're not going to details about outputs as well, since we also learned a little about these in the last part of our workshop. Okay. So the very first thing, like I've said earlier, is to import PyCPLEX. Downloading PyCPLEX can be a little difficult at first. So downloading and linking PyCPLEX with Python is sometimes not that straightforward. Maybe, I don't know if you've been able to do this. And the polls did reveal that some of you were able to actually download and use PyCPLEX successfully. But it's okay if you haven't done this. And as Rose said, we're going to go over maybe some instructions that might be helpful for you later on today. But before I move on with this package, I want to talk about an alternative module that you could use with PyCPLEX. So this is called DoCPLEX, but we're not going to get into the details about DoCPLEX today. And I think there are a couple of reasons why we might, as researchers, prefer the PyCPLEX package over the DoCPLEX package. So the PyCPLEX package is actually really useful because it does use the PyCPLEX callable library, the C API. And those of you who have worked with other programming languages in PyCPLEX before, you might recognize this from that, basically. So all the functions and all the classes that are available to us in the PyCPLEX callable library will be available to us through the PyCPLEX module. And this is something, of course, as researchers, is something we desire, basically, because there are many functions that will help us change the solution procedure. You can use advanced functions like callbacks, or you can just retrieve solution information in a more detailed manner. Likewise, you can monitor the solution procedure in a lot more detail if you're using some of the functions and parameters that are available to us through this library. So it might be useful to prefer maybe this over DoCPLEX. But again, if you maybe want to look into it, it's definitely an option and it's out there. And once you download CPLEX, this should be available to you too. So I will just direct you to the links for this if you are interested in that. But today we're not going to get into the details of DoCPLEX. So this is just like a little warning that I wanted to do before we move on. And actually, if you've again used CPLEX with another programming language before, the functions that we're going to talk about today will probably be very familiar to you. Yeah, so this is also something to keep in mind. All right. So let's just start building our first model. Let's just look at a very, very simple LP model with a very obvious optimal solution. So the motivation behind actually me introducing you this extremely simple LP model is to just showcase the functions that we will be using. And we're going to sort of build our way up into a more complicated model as we go. And we're going to learn what kind of changes we have to make to the arguments in these functions that we will just learn about just now as the models get more complicated. Okay, so again, this is a very simple model. We only have one decision variable, x, and we're trying to maximize it. And we only have one constraint where we just say x has to be smaller than 10, and x is a continuous variable. So following the sort of template that I've shown you earlier, the very first thing we are going to do is to initialize data. So the very obvious data that we have here is the right-hand side of our constraint, right? So this 10 that you see on the right-hand side of that constraint is something that we might want to initialize. The next step is to initialize a CPLEX model object, which basically is going to be this C, which you see here. We're first going to call our module CPLEX, and then we're going to say create a new CPLEX model object and assign this to C basically. And that's just going to allow us to have an empty model. Since our model is currently empty, we want to add variables and constraints to it as we go. Oops, let me clear that. Perfect. So initializing variables is available to us through the variables.add function. And there are going to be a couple of arguments that we will need to pass into this function for us to be able to do this. Namely, these are going to be what the coefficients of these variables that we have in the objective function are, and the names of the variables that we're wanting to introduce. An optional argument, but if you're working with MIPs, you have to have it in the arguments section, is whether the variables are continuous, integer, or binary. So if you have to make that sort of differentiation between different variable types, you will have to add an additional argument inside this function. And I'll show you an example of this like in the next slide, but since this is an LP, we don't really need to actually specify whether these variables are integer or binary since they're not. Okay, so the names argument is again a string, a list that consists of strings, and the objective function coefficients, which is basically the argument you see here called obj, is again a list, but this time it's a list that contains numeric values. So as we will see later on, this sort of list structure that we're passing into these arguments will be useful later on, and keep in mind that some arguments will take lists that contain numeric values, and some lists will take lists that contain maybe strings. So this is, again, going to be really important later on, so that's the reason why I'm like stressing it a lot. Perfect. And the reason why we are introducing both x and 1 as lists and not just on their own is exactly because of this, because we have to follow the syntax, and we need to pass a list into objective and names instead of individual values. So if x and 1 were not lists and just values on their own, this would just raise an error, and CPLEX would not understand what we're trying to do. So it's important to just keep that in mind. So this is what I was talking about regarding the types of the arguments of these variables that we have to define. So types is an argument that you would basically add into this function where right after add, if you want to specify if your variable is integer or binary. And something that I've come across as I was building an LP model once is if you specify the type of a continuous variable to be continuous, just like this first bullet point that you see here, PyCPLEX actually ends up turning it into an integer program, which it isn't because all your variables are actually continuous. So explicitly defining continuous variables in an LP is not a good idea. And it might actually cause some errors in your code. So you don't really need to worry about this again if you're working with a linear program, and only just utilize these typed arguments if you're using or if you're trying to implement a integer program or a mixed integer program. Perfect. So let's just get into initializing constraints. For this purpose, we're going to be using the linear constraints.add function. And just like before, this function is also going to take some arguments. And namely, these are going to be the linear expression that involves our decision variables. And we're going to see what we mean about this in a second. Secondly, we're going to have to specify if it's a less than or equal to, or greater than or equal to, or an equality constraint. And then we will have to tell PyCPLEX what the right-hand side of the constraint is, of course, as well as the name of our constraint. So sometimes the first bullet point where you see the linear expressions can get a little messy, but there's a nice class that sort of allows us to do this more in a more structured way. And it's the Sparse pair class that we have available through the PyCPLEX module. And we can just call this class by saying from PyCPLEX Sparse pair. And in this presentation, I'm going to use this because, like I've said, this is really, I think, speeding things up and just making things more structured and it's easier to follow. Okay. So the linear expression argument that we have over here is going to contain everything that has to do with our decision variables. So all the decision variables that you have in your constraint will have to go inside this linear expression, which again is going to consist of sparse pair expressions. The sparse pair expression is one where we have either one or multiple decision variables, basically. And one thing to keep in mind is that the sparse pair expression just consists of two different arguments. The first one is the index argument, which is going to store the name of the variable that we're wanting to call. And the val or the value argument is basically the coefficient of this variable that you want to include in that linear expression, basically. Like I've said, you can call multiple decision variables inside the sparse pair argument if you want, and we're going to get into details of how to do that later. The second argument in the add constraints function that we're going to look at is, and whether it is a greater than or equal to or less than or equal to constraint. And for this, we're going to use senses. And again, we're passing lists into each one of these arguments as well. So like I've said before, it's important that we keep this in mind because this is going to be the case for most of the functions that we're using with PyCPLEX. So you can see that what we're passing to linear expression here, this entire thing that you see with sparse pair, is a list. The same thing goes for census. So this is going to be a list of strings. And again, the same thing goes for the right-hand side, which is going to contain the numbers on the right-hand side of our constraint. Or you can, of course, do this by using a predefined list, which we had done in the very beginning of our talk. And the same thing goes for the names argument, which is basically the names of your constraints. So this is also a list that you have to pass into this argument. Okay. So this is just something to, again, keep in mind. Okay, so let's just have a look at how things look like overall. So we're wanting to add this constraint. If you remember, x is less than or equal to is everything that we're trying to do here. The very first thing that we have added is the linear expression, And we're using the Sparse pair class to basically populate that expression that we're trying to have in the left side of our constraint, which only consists of one variable again, which is x, as you can see over here. So it will only consist of x, and it will have a coefficient of 1, since our constraint looked something like this, if you remember. So we have a coefficient of 1, and we only have one variable, which is x, which is again defined through the sparse pair expression. The next thing that I'm telling PyCPLEX is that this specific constraint is a less than or equal to constraint, which it clearly is. So this is basically referring to that. The next thing I'm telling is the right-hand side, which is basically 10. But this is, again, don't forget, right-hand side is a list. So this is referring to that 10. And names is the name of your constraint. So I decided to call this constraint 1, but you can just call it whatever you find suitable in your model. Perfect. So this is how general things will look like with this constraints or linear constraints.add function. Perfect. So now we've added all the constraints and variables that we need to add. And before we solve this model, we might need to tell PyCPLEX whether this is a minimization or a maximization one. This is clearly important because if you don't mention the correct one, it will cause obviously problems and it will not give us the correct solution. And to do this, we're using a function called objective.setSense. And this is basically telling PyCPLEX, I want this to be a maximization problem. So what you see over here, actually, this entire expression inside this function, the c.objective.sense.maximize, is basically our way of saying, hey, PyCPLEX, I want this to be a maximization problem. So you're passing this inside that, and PyCPLEX will understand that this is going to be a maximization problem once you do that. And you could do the same thing for a minimization if you want. So you could say .minimize if you want to explicitly define that. Perfect. So once we have this, we can go ahead and solve our model, which is, again, see if you remember from earlier on. And we're going to solve the problem by using the .solve function that is available to us. And once we just add this line and solve the entire thing, you're going to see that in your console log, there's going to be the solution log. That is something that is similar to the PyCPLEX Studio IDE. If you ever used that before, this will be very familiar to you. So it's just going to give us some information about what it's doing, where it's at with regards to the solution procedure. It's going to give you all the details that you need about the solution procedure, pretty much. There are ways to disable, enable, or make this more or less detailed. And we're going to talk very, very barely about that at the end of the talk when you get to parameters as well. Perfect. So we have successfully solved a very simple PyCPLEX problem now. And we have written our model and everything works fine. And what we might want to do next is to actually understand what our optimal solution looks like. And in this case, retrieving solutions is, of course, what we need to do. And to do this, we can use the function solution.getValues. And this is basically going to get us the optimal values of the variables that we pass inside that function. So we have this function, as you can see here, c.solution.getValues. And this x thing that we're passing it is basically the name of the variable that I want to know the optimal value of. So whatever you pass here is what x solution is going to be set to. So this c.solution.getValues is, again, getting the optimal value of x and then passing it on to the x solution variable over here. And once we've done this, we can just print x solution to see what it is, or you can write it into a file if you would prefer that. And just like we have seen in the very simple model, our solution was really straightforward, and we know that x is going to be equaling to 10, of course, in an optimal solution. And we can do the same thing for the optimal objective function value, but this time the function that we're going to call is going to be a little different. Instead of solution.getValues, this time we're going to call solution.getObjectiveValue. And this time we don't really have to pass anything inside this function because it's just the way the function is defined, and this will basically return the optimal objective function value to us and then assign it again in a similar manner to the variable objective. And then you can go ahead and just print that, and obviously it's going to be the same as what we've seen earlier since the objective function was simply x itself. Perfect. So from here on, things will start to get a little more complicated, but we're going to use the same functions and the same arguments as before. We're only going to look at some variations that are often things that we see in our problems to just give you an idea of how these things look like. So let's assume that we have multiple decision variables. This time, namely x is going to be defined with an index of I, which ranges between 0 and n-1. And again, we're trying to maximize this, but this time we also have a coefficient for the variable x in the objective function. And as for the constraints, this time we have multiple constraints basically for each value of I, and we want to initialize every single one of these constraints basically. So let's have a look at how we can do this. Okay, so yes, so before we actually move on, we need to take care of initializing some of the inputs of our model, basically, like we've talked about before. Namely, we're first going to introduce, this AND and A parameters. And is again the range in which our decision variables are going to range. And A is the coefficients, basically, of these variables in the objective function. The next thing that I need to do, since this is going to be a brand new model, is to define my model from scratch using this expression. And the next thing that I'm going to do is to add variables to this new model that I just created using the parameters that I've just initialized. So we know that the coefficients of these variables are going to be 5, 10, and 15, like we've seen before, since they will take this A value as a coefficient. And this objective argument is basically just doing that. So we're passing this list into here to just say these are going to be the coefficients of these variables in the objective function. And the second thing I need to do, if you recall from before, is to identify the names of the variables that I'm introducing. So what is different here is that we're using a list comprehension, if you recognize from last week, instead to basically initialize our names. So what this comprehension thing is doing is that it's iterating I in the range of n, which again, if you recall from last time, is going to change between 0 and n-1, and assigning a single value to I every time it iterates in that loop, basically. And it's going to build that list up by going through that for loop, simply. So this is going to return us a list of size 3, since we've defined n to be 3. And it's going to end up giving us the names of these variables, again, x1, x2, sorry, x0, x1, and x2. Perfect. And this is like a very, very general way of putting what things will look like. So one thing that we need to, again, be careful here is the size of these lists. So we've already said that we have to pass a list that contains either numbers or strings, depending on the argument. And the sizes of these lists that you're passing to variables.add have to be consistent. So for instance, if A was a list that had, I don't know, 5 different values instead of 3, and names was still a list that consisted of 3 items, CPLEX would raise an error saying that, oh, I don't know what you're trying to do because you're passing me 5 different values for objective, but 3 different values for names, and they just don't add up. And it will not know what you're trying to do, so you will have to make sure that these lists are consistent. And regarding that, the second thing that you have to be careful about when you're adding these arguments is the ordering of the variables. So when you're using list comprehensions, the order in which you introduce these for loops is going to be very important. And we're in fact going to talk about that in one of the upcoming slides. But what I mean by that is the first element in the list that you're passing into names is the string that is associated with the first member of the list A. So, and likewise, the second member is going to be associated with the second number, and the third one is going to be associated with the third member of another list. So it kind of works in that way, and you shouldn't mess around with the ordering of these variables if you want it to work correctly. So this is also something that you need to keep in mind. It might sound very trivial and very straightforward for this example, but later on, you will see what I mean by this, I think, when you have multiple variables with more than one index, maybe things might start to get a little more messy. So it's something that we need to keep in mind. Perfect. So let's just have a look at our constraints this time. So we have this constraint xi is less than or equal to bi. And just like before, we will have to introduce what b is first before we move on. And let's just do this by just utilizing, again, this expression right here before we move on. And one thing that we need to be careful about in while we're actually introducing these constraints is, again, the size of the lists that we're passing into the function. We will see in a second. But we're going to be using the same function as before. So we're using linear constraints.add again. But our arguments will look a little different. And I will just walk you through what I mean by that in the next slide, actually. The things that you see in this slide and the next slide are basically the same. But I think this one's just nicer to look at overall, and it's easier to see the differences, I believe. So this time, in our constraints, we have multiple constraints that we want to initialize at once. So that's the reason why things will look a little different. So let's have a look at the linear expression line, the first argument, basically. This time, instead of just introducing one sparse pair expression, which is basically what you see over here, we are introducing a series of sparse pair expressions by using this list comprehension syntax that we have available in Python, which involves this for loop, basically. And I is going to take different values again in this range of n, ranging from 0 to n-1. And as n iterates within this loop, it's going to basically assign different values to what we have inside of our sparse pair expression. It's going to assign different numbers to I and different names, basically, of variables inside this sparse pair expression. And every expression in this linear expression list that we have is going to correspond to one constraint, okay? This is going to create a linear expression list that, again, consists of different sparse pairs, which is going to be something 3. So yeah, that's what things will look like for us. And what we're doing inside the sparse pair expression is, again, the same as before, but just with a different syntax this time. We are calling the variable xi, which here again, I is going to take a different value based on where it is in the loop. It's going to call this variable, and then it's going to multiply this variable with whatever you have on the other side, and then add that to basically the linear expression list as we go. The second thing that we want to pass into this function is the census argument, which is, again, the same as before, but the only difference is that now we have to multiply this with n, which means that we're going to have a list that consists of the expression L n times. So it's again going to be a list of size 3 in this example. And we can just pass b into the right-hand side expression straight away because b is a list of 3 numeric values anyway. And the names argument is going to look very similar to what we had seen before. So we're just going to range, again, in between this range of n values, and we're going to assign the values of I into what you see over here. So each constraint name will be different from one another. And this list also is going to consist of 3 different values. So again, both the linear expression, the census, and the right-hand side and the names arguments are all going to have lists that are consistent in size and that are ordered in the same way as well. Perfect. So that kind of gives us an idea of how we can do this. So let's just make things a little more complicated and see how things will change. If you have variables that look like this with two different indices that range in different ranges, things might start to get a little complicated. So let's just assume that we're changing our objective function into aij times xij, again, a summation of all of the values that involve basically this, these decision variables in A. And this time we're going to have more constraints as well, because again, we have this new sort of index or new range that we have to range in called j and octa m minus 1. And let's just say that we have m equals 2, which is again going to define how big this part of the model is going to be. So this time we need to make sure that we define A and B all over again, because again, they look different from before. They have two different indices, both of them. And oftentimes, what you will see is a syntax that looks like this. So if you're reading your data from maybe a file, or maybe you want to define this way for whatever reason, we will have to do some tricks to basically get over some of the problems with passing only a list that contains numeric values into CPLEX. What I mean by this is if you try to pass A, as is right now, into CPLEX, it's going to raise you an error saying that it can't understand what you're trying to do. And this is because we have said earlier, this list is going to consist of numeric values and not lists. However, the list that we're looking at right now, the list A, is a list that contains lists. And this is not what we want. We want numeric values in this list, or at least CPLEX wants numeric values in this list. So we will have to convert this list into a form that looks like that. So you can, again, if you don't use this to initialize your data or to generate your data, you can straight away start using a list that looks like this. It will definitely make your job easier when it comes to passing arguments to CPLEX. But again, it might be harder to read if you especially have more than two indices. So if you have 3, 4, sometimes, you know, our models can get very big, and it might be really hard to understand which one is which and what you're referring to, and things can get messy. So this is just something, again, that we will have to keep in mind for later. So our objective function, again, will look something like this. And we've already defined A to be a list of lists. And now we're going to look into how things will look like when we're using the variables.add function. Again, since we're using a new model, we will have to initialize a new model. And then we're going to go ahead and use our c.variables.add expression here to add the variables into our model. Let's just start with names this time, and then I will tell you what we're doing in the objective argument. So this time, names looks very different to before, to what we've done before. But we have an additional argument, j, which again ranges in the range of m. And yeah, this is the only difference. It's still using the same list comprehension structure. There's nothing different in the way we're doing it. Awesome. So regarding the other argument, the objective argument, we're using the sum function, which is a little different. We have not done this before. So the reason why we're using that actually is because we want to change our list of lists that you've seen here. So basically this thing over here into this form. And that is going to allow us to do that. So that's actually a really fast way of overcoming this problem of passing a list of lists into that argument. So the only use, again, of that sum function is going to be to use a list that consists of numeric values right into the function. So that's, yeah, so that's exactly what we're doing in there. And once we've defined both of these arguments, we can just go ahead and add our variables. Perfect. So we have a set of constraints now that we want to define, and we will have the same problem with B as well, since this is also sort of dependent on both I and j at the same time. So you might initialize your variables in this way, or your parameters, sorry, in this way for whatever reason. but we will have to change them into, again, this form that you see over here. I can't see the entire thing because there's a zoom thing that's blocking it, but that thing has to be what we're basically passing into PyCPLEX. And this is our initial list of lists again. So we will have to convert this into that. And let's see how we can do that. So our constraints, again, will look like this, where we have different x variables and different values on the right-hand side. And again, we're going to be using the linear constraints.add function, nothing different with that. But this time around, the sparse pair expressions will look a little different. So the only difference here is actually that we're having a for I in range n argument here, along with a for j in range m argument followed by it. And this is only because we, again, want to populate this list for both I and j. And that's the only difference between what we have done before and now regarding the linear expressions. As for census, we're going to have more constraints that we want to add. And this is going to be of size n times m, since, again, we had oral arguments for both of these ranges. And we're going to do the same trick with b here regarding the sum function. Again, exactly the same purpose, nothing else, other than just changing b from a list of lists into a list of numeric values. And the same thing for names, so nothing will change in terms of that. I mean, except for the new argument that we have here, which is j. And one more thing that I need to again stress is the ordering of values that you're adding into these lists. So everything has to be ordered in the right way for your constraints to be correct. So the first sparse pair expression, again, you're adding into the linear expression list have to be the first name that you're assigning to it, or have to be the first right-hand side value that you're assigning to it. So everything sort of works in the same order when you're using this function. And this is something, again, we will have to be very careful about when we're working with bigger models, since they can get very complicated very easily. In some cases, we will have a summation expression inside our constraints, just like this one. And let's just have a look at how we can do this and what we will have to change to do this. Since we've ditched the I on the right-hand side of the constraint this time, we only have a single value called dj, which is changing in, again, the range of j. We are back to using lists that look like this just naturally. So we don't really need to worry about converting it into a list of numeric values because it's already a list of numeric values. Okay. And how we can do this actually is, I'll just show you in the next slide because it's nicer to see it that way. So this time, what is different here is basically the sparse pair expression, the linear expression that we're looking at is, I think, the most sort of complicated thing out of all, and the rest are a little easier to follow. So we still have this for j in range m expression outside of the sparse pair expression, but this time our for I in range n loop is inside the sparse pair expression, as you can see. So we're calling all the i's that are in range n inside the sparse pair expression this time. And we are also passing a different list this time into the values argument of the sparse pair. This is because we have n different values this time that we want to add into this linear expression. And let's just go back to the constraints to see what I mean by that, and clear that as well on the way. So we were going to do the summation based on the index I. And we were going to repeat our constraints based on the index j. So this is something that we should keep in mind before I go back to the slide that I've just shown you. So the constraint will repeat itself for all the values of j, which is basically what we're doing right here. But the linear expressions that we're having in each one of the constraints is going to be for all the values of I, basically. We're going to just sum everything together. And that's what is allowing us to do that. And this is basically just the coefficients of these variables that we're passing, again, inside this sparse pair expression. So the only thing that changed is where we place this for loop, really. But a small change in where you place it changes the constraint entirely. Yeah, so this is kind of the general idea. And this time, instead of having senses L times N times M, we only have times M. And this is because, again, we have this for arguments sort of outside the linear expression. And it's also because we have M different constraints this time. We can just assign a list to the right-hand side like we've done before. And we will do the same for loop over here, just like before. So again, we have to be careful about the ordering of all our variables. Yeah. Perfect. So I think that gives us an idea of what our models will look like. So let's talk about the parameters now. So you've written your model, everything works fine, but you're just curious about maybe you want to change certain things about the way your solution procedure is, and you're curious about how this could affect your model. In this case, you might want to change some of the parameters that are available to you through the CPLEX module. One thing that you need to make sure actually regarding these parameters is that you should call these, I mean, if you want to change them, that is, you should do that change before you call the solve function so that your changes will be applied to your model. And sometimes these parameters can be a little overwhelming because there are actually so many of them that you could change and that you could see. And a good way, I think, is to see all the parameters that are available to us is parameters.getAll function. And that will basically return you all the parameters that are available to us through CPLEX and their default values. So these will be set to some default value at first if you don't change them afterwards. So let's just have a look at it. Again, like I've said before, we can just use this parameters.getAll function to do this. And this is a list that, I mean, this returns you a list that is, I think, if I'm not misremembering, it was around 180 different values, I believe. So there's so many parameters that you could change, like I said. But let's just look at a small portion, just 5 of them, I think. So for instance, in an MIP, you might want to change how aggressively you want to generate cuts. Right. And this, these parameters will allow you to do that, basically, these things that you see here. So there are different types of cuts that you can call for this purpose, again, from CPLEX. And yeah, these are just some of the examples to that. And I think, by the way, what you see here regarding 0 is default value for these cuts. So I think 0, if I'm not wrong, is the default value for all of these cuts, where CPLEX will decide how aggressively it wants to generate these that belong to these classes. Some other examples are, for instance, you might want to change the number of nodes, maybe that you're exploring for whatever reason, or you might like to change maybe the MIP gap if you're looking for something that is close to optimal, but it's okay to be slightly suboptimal maybe, so you can change it the way you want. Same goes for the integrality conditions that we're defining on the MIP. And to change these values, we can use the function parameters.mip.tolerances mipgap.set something. So this is specifically for the MIP gap. So this will be different. And also these things, each one of them will be different based on which parameter you're trying to change. So this is, again, only one example of how you can change maybe the MIP tolerance in this case. So this will set it to 0.01 instead of the default of, I think, 0.00001 or something like that. It's way smaller than that in the default form. So there are many different parameters like this that you could check out for your own if you want. And IBM's CPLEX parameter reference is great for that purpose. So, yeah. So now let's move on to debugging before I wrap everything up. This is really important to to be aware of, I think, when we're building our models. And this is because oftentimes, even though we think that everything works fine, there are no errors, it looks great, it is very likely that there's an error. Sometimes, I mean, depends again on how complicated your model is. In these cases, it's a good idea to write out your model as an LP file so that you can visually see what you're doing. I've used this many times before to sort of debug my codes, and I think it's just the most intuitive and easiest way of understanding what you're doing and to double check what you do. Once you have this LP file written out, you can then open it in the CPLEX Studio IDE, which is something that already comes installed when you install CPLEX, and you can just open it and then drag the LP file that you've just generated into the CPLEX Studio IDE, and then it will open it. And it will look something along these lines. And then you can specifically check which variables assigned to what constraint and how they look like in the objective function. So yeah, I think this is really, really useful actually for debugging. As always, we love Stack Overflow. I think I've already said this in the first part of the workshop many, many times. Although I must say for CPLEX, you might not find as much on Stack Overflow, but there are still sometimes a few posts here and there that will be very useful. And for those of you who don't know, there's also an operations research Stack Exchange page that is really great for not just CPLEX, but your operations research questions. There are some interesting discussions there if you want to go check that out. Also, IBM's decision optimization page is kind of like a forum where you can post your questions or you can see other people's questions and maybe find answers to your own questions as well. And of course, what I've talked about today is a very, very basic introductory set of functions that will be useful to you. But it's definitely not limited to that by any means. There's so much more that you can do with CPLEX, and everything is covered in the user manual that's available in this link. And if you want to look into more advanced methods, maybe you might want to go check that out. So perfect. I think that brings me to the exercises. Let me just quickly and briefly go over what we're going to be doing in the exercises. So we're going to have an MIP that looks very messy. I mean, not very messy, but messier than before, at least. And we're going to try to basically implement this in CPLEX and see how things go. And by the way, I must say this MIP does not really have a verbal explanation that I can give to you. It's just an MIP that I wrote to learn CPLEX and how different functions can be used. So that's the sole purpose of the MIP. And there are some steps that, again, we will have to follow, and this follows exactly the same template that I've shown you. We will have to initialize some of the parameters, sorry. And maybe going back to the random generation of these parameters could be a nice thing to do. And then we will import our module, add variables, add constraints, and solve everything that we need to solve. And finally, we're going to export it and see what our model looks like and if it's correct. So I think this just concludes everything that I have to say.
Thank you, Oiku. Thank you so much for your presentation. And I guess this is the time where we literally roll our sleeves and try to implement what we had.